Hey there! Welcome to a short video about gases, and we're going to start off by talking about gases with the kinetic molecular theory. The kinetic molecular theory is this concept that all particles are in constant motion, and something that you really need to know here is most likely is the definition of the kinetic molecular theory, and that within a balloon or any room that you're in, these gas particles are in constant motion and they're moving and they bounce off the walls and start moving in other directions. So make sure you pause the video and write this down. Now, there's a lot of vocab and just basic facts in this short video. Please take the time to pause the video and write down the definitions as we discuss these. So we want to talk about real gases and ideal gases, and there's actually a difference between the two. So a real gas is one that does not behave like a hypothetical ideal gas, and we're going to learn a lot about what ideal gases are. So again, understand that ideal, they're almost somewhat imaginary in that you're not really going to find them present on Earth's surface, just with regular atmospheric conditions, but it's good to think of them in this ideal way. It simplifies things for us, and hey, you know, in chemistry, we like it simple. Keep it simple. So something we will be talking about a little later is this ideal gas law equation, PV equals nRT. You're going to see this a lot. We're not worried about it too much right now, but it's a good just to see that as an introduction. So when we're talking about gases and we're talking about the kinetic molecular theory, we talked about that gases can basically collide with one another. And there's a few types of collisions that basically you should write down. You don't have to write the whole definitions down here, but understand that an inelastic collision is one where the final kinetic energy is less than the initial kinetic energy. So basically the energies do not equal each other. Perfectly inelastic collision is one in which the bodies stick together. So this is good to understand that a perfect inelastic is where they stick together, and that an elastic collision is between ideal elastic bodies in which the final initial kinetic energies are the same. So that's kind of where it's saying like energy 1 equals energy 2. In that example. So you can see down here we're talking about their energies being equivalent to each other in an elastic collision, and this is one that we're going to talk about probably the most in using collisions for the types of gases. So there's a lot on this screen, I know that. I'm going to fill this in though. So kinetic molecular theory of gases, this is again talking only about ideal gases. There are 5 postulates to the kinetic molecular theory, so we're going to go ahead and fill this in. So there are a large number of tiny particles very far apart, right? Understand that they are very far apart relative to their size. Collisions between gas particles and container walls are elastic collisions. Gas particles are in continuous, rapid, random motion. There are no forces of attraction between the gas molecules, and the temperature of the gas depends on the average kinetic energy of the gas. So we have our equations here. K equals 1/2 mv squared, where m is mass and v is velocity. It's important to note here that all temperatures are going to be measured in kelvins. We're going to talk about kelvins in a moment here, but it's a new measurement of temperature. Notice there is no degree sign. with Kelvin, so it's just K. And Kelvin, the way what Kelvin actually equals is your degrees Celsius plus 273. So you just simply add 273 to your given degrees Celsius, and you're now in Kelvin. So a few fill in the blank here terms that we want to look at is all gas at the same temperature have the same energy. And lighter or less massive gases will travel faster. So if the particles move faster, then the temperature increases. If the particles move slower, then the temperature decreases. And you guys can see that that's a direct relationship. And again, we're deriving this from the kinetic energy equation up here, 1/2 mv squared. If I have a heavier object, it has to travel a little slower to have the same energy. So that's being at the same temperature. If it's a lighter object, so m goes down, v has to go up, meaning it travels faster, again, to have the same energies. And that's really what Kelvin's is Kelvin measures the motion of particles. It is a measurement of how much energy they have. So it's the energy of particles. Take a quick look here at real gases. Again, we mentioned earlier there's ideal gases and then there's real gases. So this is your real gases here. These do not strictly obey the ideal behavior of a gas. They do occupy volume and have an attraction to one another. They can be compressed or cooled, and then they liquefy. And the most important one here for number 4, I want you to big star this here, is they behave like ideal gases when pressure is low and temperature is high. That's when the molecules are furthest apart. I remember it as low P, high T. So a question I'll ask you is, when does a real gas behave like an ideal gas? Right here. Low P, high T is when an ideal gas behaves, or a real gas behaves like an ideal gas. So continuing along here with our notes, we want to talk about properties of gases. How do gases act and behave? And some important points to remember here is that gases take the shape of their containers. They have no definite shape or volume. Gases have low densities. They are highly compressible. I can squeeze a gas to fit it into a very tiny, small place. They do mix readily and diffuse, and gases also effuse. Now these are two vocab terms here, diffuse and effuse. I'm going to change the color a little bit. Vocab terms that we will be defining in a moment. So we'll get the definition of those. And one quick thing to note here is that a fluid, we think of fluids as only liquids, and that's not true. Both a liquid and a gas can act as fluids, because a fluid is anything where they are able to freely move past one another. So since they're able to do that, like a liquid or a gas, they take the shape of their containers, they're able to flow. So gases are considered to be a fluid-like substance. Here's our definitions of the diffusion and effusion that I was talking about, that I said you were going to need here. Diffusion is a random movement of your particles from an area where their concentration is high to an area where it's low. So a good example of this is something like a bottle of perfume. Here, if you open the lid of the perfume, and in here we have our perfume, those are my perfume molecules inside the bottle here. If I open the lid, they are able to just kind of come out and fill up the space that they can occupy, so up into the room. Whereas effusion is a process by which gas particles under pressure pass through a tiny opening. So again, I take that same perfume bottle with my little opening on it, and instead of opening it, it's a spray. So this is a spray bottle, and the gas particles are going to be sprayed out in more of a direct line, kind of misted. So this is just open, and this is a spray. So if you spray them through this tiny opening in the top of the bottle, that's effusion. But if you just let the bottle of perfume open and just let them kind of diffuse through the room, that's diffusion. Again, that's kind of explained down here in these two pictures that you can see. Fusion, if you would put a little pinhole in your balloon, all the air would try to escape out of that one little opening. Whereas here, diffusion, if you were to open this and then just let them kind of move through in back and forth, that's diffusion. So it's important to understand those two concepts because they apply a lot to what we're going to talk about of how gases move through the air. All right. Goes hand in hand with gases, and we're talking about maybe the atmosphere, and we're talking here about pressures. What is pressure? And you need to know here that pressure is going to be the amount of force exerted per unit area of a surface. So area of a surface there is what you need to know. So like the gas inside of a bike tire exerts a pressure on the walls of the tire, it keeps the tire inflated. Think of this is the gas inside of the air tire, and every time it hits the wall, it's moving, it has some mass, gas has mass, it actually does, you will calculate that later, but it exerts a force on the tire. And you got to think you have all of these hitting the tire walls at the same time or at different times, but they're all exerting this force on the outside of the tire, which keeps it inflated and doesn't allow it to kind of deflate. But that's important to understand what pressure is. We kind of have an equation for pressure. Again, pressure is force divided by area, so force per area. You might ask, well, I've heard the weatherman talk about pressures before, and they measure the atmospheric pressure of the day. You might have heard like there's so many atmospheres today, and what they use to do that is a barometer. And that's basically, you need to know here, a barometer is your device used to measure atmospheric pressure and air pressure. So here's an example of this. And basically what you have is a bowl, like a container of some sort, and the air pressure pushes down on the container, and it actually forces the mercury up the tube or water, whatever it is, and you're able to measure that just like you would a ruler, and that's your pressure of the day. I actually have a short video clip for you to watch that shows us what a barometer is and how it works.
Barometer. The pressure exerted by a gas is measured with a device called a barometer. This device can be assembled very easily. For this, we need a long glass tube of 100 centimeters, closed at one end and with a narrow bore at the other. This barometer is filled completely with mercury. It is up-tuned gently into a pool of mercury. When the barometer is inverted, an empty space is created by the tube. This length of the mercury level in the tube is measured starting from the reservoir level. The length of the mercury column is equal to the pressure exerted by air. Under the normal conditions, the pressure is 76 centimeters or 760 millimeters of mercury at sea level. The pressure is measured and represented in terms of atmospheres. 1 atmosphere is equal to 76 centimeters or 760 millimeters or 1 torr. The pressure of air is generally lower at the tops of mountains and at hill stations as compared to that of the pressure at sea level. The pressure gradually decreases the higher the altitude.
So at the very end of that segment, they talked about the pressure being lower on top of a mountain than necessarily down on a beach or at sea level. And that really just has to do with the amount of air that you have stacked on top of you. The higher you go up, or higher altitude, means the lower pressure. That's a less amount of air you have sitting on top of you. And when you're down at sea level, you almost have 60 miles worth of air sitting on top of you. And we don't think that air is that heavy, but when you have that much stacked up on top of you, it really can be quite heavy. And again, we saw in the video that 1 atmosphere is at 760 millimeters of mercury, which is typically what you're going to find at sea level. So again, here you're seeing that 760 millimeters of mercury is your standard atmospheric pressure. And again, just knowing that what a barometer is and does is really significant and important for measuring pressures of atmospheres. There's one other device that we use to measure pressure, and it's called a manometer. And a manometer or manometer is used here to measure the pressure of an enclosed gas. So a lot of times you're going to be using this in the lab where you have a specific gas that you want to find the pressure of, and you have some vacuum in here, and this is a pressure of oxygen gas in millimeters per mercury. And what we can do is we can actually measure that. So taking a look here, this is a little better example of a manometer. So you have your unknown pressure of a gas that's coming into this U-shaped glass tube. So this is your fluid of interest, or gas in most cases. Remember, gases can be a fluid. And you're going to measure how much it pushes up on the other side. So this h, or height distance here, can be measured. And you can gauge the pressure, which is the change in pressure, is your initial pressure, which is given, so you know your initial pressure, and your P, which is your unknown there, to kind of determine the values there within your manometer. So that's just a unique another way to measure pressures, and it's just something important that you should know and be able to identify that, hey, this is used to measure pressure. And then while we're talking about pressure, we want to talk about these units of pressure here. This is something that you should probably copy down, and you do have, but you want to absolutely make sure you get this filled in that we're going to look at some of these major conversions that we need to know here. So these are all units of pressure: pascals, millimeters of mercury, torrs, atmospheres, and psi. So the best way to kind of take a look here at these is to fill in some of these conversions. You need to know 1 atmosphere is our 760 millimeters of mercury. 1 atmosphere also equals 760 torr. So millimeters of mercury and torr are equivalent. 1 atmosphere is going to equal 101.3 kilopascals, and 1 atmosphere is 14.7 psi. Sometimes you will be asked to convert your atmospheres, and here's a sample problem real quick. So you have this down in your notes. We need to convert 1.75 atmospheres to kPa. So I set up my conversions, set up my train tracks. I'm going to bring down atmospheres, and I'm going to kPa. So that's on top. So 1 atmosphere, up here, if I look, 1 atmosphere is equal to 101 kPa. So 1 atmosphere is equal to 101.3 kPa. See here, once you take 1.75 divided, or times, I should say, by 101.3 kPa, you get 177 kPa. And then it wants you to convert that to psi. So if we take our 177 kPa and set it up, I'm going to cancel my kPa by bringing that down, and I'm going to psi on the top. And 101 kPa equals 1 atmosphere, and 1 atmosphere equals 14.7 psi. So therefore, 101.3 kPa equals the 14.7 psi. So I'm going to put in my 101.3 down here and my 14.7 on top, and I can simply grab your handy dandy calculator and take my 177 times 14.7 divided by 101.3, and we get 25.7 psi as your pressure for this conversion. So that's simply how you apply the conversions for your calculations, and you will be asked to do that from time to time in different word problems. The last thing I'm going to leave you with here is talking about STP, so a thing that you need to know for standard temperature and pressure. Highlight this, star this, know this. The conditions: 1 atmosphere or 760 millimeters of mercury at 0 degrees Celsius, which is equal to 273 Kelvin. Note, there is no degree sign for kelvins. It's just Kelvin, just K. And also, if you want to jot this down in your notes, at STP, 1 mole of gas occupies 22.4 liters. That would be a good thing to have, because we will use that a little bit later when we continue talking about the gas laws.